In this video, we're going to talk about the relative reactivity of aldehydes and ketones with regards to nucleophilic addition to the carbonyl carbon. And then we're going to be introduced to acetals and hemiacetals. So first we have our aldehyde and our ketone. Now, when you think about nucleophilic addition, one of the first things that you probably remember from SN2 chemistry is that if there's a lot of steric hindrance, a nucleophile is going to struggle to get to its target. So the aldehyde is less sterically hindered, and the ketone is more sterically hindered. That's a point for the aldehyde here. It's going to be a lot easier for a nucleophile to get in to attack the carbonyl of an aldehyde because the hydrogen is not as big of a group as any alkyl group would be. Even a methyl group is much, much larger than a hydrogen atom. Our next thing is that alkyl groups are electron donating. So this alkyl group is donating electron density towards the carbonyl. And if something is going to be electrophilic, we actually want electron density being pulled away from it in order for it to be more reactive. So the more electron density that's flowing into the structure, the less electrophilic it is. So the ketone has that going against it because it has twice as many alkyl or aryl groups donating electron density towards the carbonyl carbon. So this is a point to the aldehyde again, because essentially this carbonyl carbon has a much larger partial positive than this one. So that makes the aldehyde more reactive and the ketone less reactive when it comes to nucleophilic addition. Now, there's one exception here. If you have electron withdrawing groups of situents that are part of a ketone, that is going to be a little more favorable. So consider having 3 chlorines substituting your hydrogens here. This does not have the issue of electron density being poured into the carbonyl. The electron density is actually getting pulled away from the carbonyl. That makes this a huge electrophile. So we have a much more electrophilic carbonyl carbon, and that's going to make addition favorable. So this is your one exception, when you have some sort of massive electron withdrawing group as part of a ketone. So let's introduce our new functional groups here. We have hemiacetals and acetal. I want to remind you that the prefix hemi, you've seen this before. You've seen this used to describe hemispheres of the earth, right? Hemi means half, so a hemisphere is half of a sphere. A hemiacetal is half of an acetal, or halfway to an acetal. So, for example, if we take a ketone and we react with one equivalent of an alcohol, I know we have a lot of R prime and R double prime going on here, but we'll do our best to keep it straight. You can do this reaction in acid or base, and this will take you to what is called a hemiacetal. Or since it comes from a ketone specifically, this can also be called a hemiketal, but you don't hear that nomenclature used as often. Now you can finish it up with one more equivalent of the alcohol, and you will get all the way to the acetal, which can also be called a ketal. Now I want you to notice that the first conditions say acid or base. The second set of conditions only says acid. So an acetal cannot be formed in base, which means it is what we call base stable. This simply means that an acetal cannot be broken down in base, because this reaction is actually completely reversible. When we look at the mechanism, we'll go into that in more detail, but it cannot be broken down in base. Now we can also do the same thing with an aldehyde. When you react with your first equivalent of alcohol, you get to the hemiacetal, And when you react with your second equivalent of the alcohol in acid, you get all the way to the acetal. So the key thing to note about the acetal is that it has two equivalents of the alcohol added to the carbonyl carbon. The other thing that's important here is that the side product of this reaction is water. And the oxygen that's part of this water molecule is your carbonyl oxygen. So you actually end up losing your carbonyl oxygen, and the two oxygens that you see as part of your acetal actually come from the alcohol. We're going to go over the mechanism in detail in a second video. Now, this is one of the topics in OCHEM that is just directly relatable to nature. I mean, there are many, many topics in OCHEM that are directly relatable to nature, but often there aren't a lot of topics that OCHEM 1 and OCHEM 2 students have seen. But this is one that you've actually seen probably many times before. So sugars, ketoses and aldoses, exist in linear and cyclic forms. The linear form is usually drawn out in what's called the Fisher projection. And the cyclic form is drawn out in what is called the Haworth projection. Notice that the cyclic form is actually a hemiacetal. So this carbon here used to be a carbonyl. It's this one here that used to be part of an aldehyde. So this chemistry is really, really cool, and we'll actually talk about this more at another point. But it's really fun to kind of look at this and figure out where did all these different atoms come from. The oxygen that makes the cyclic acetal is actually the penultimate alcohol here. So in acid, this alcohol ends up attacking your aldehyde and creating the acetal that you see here. So it's pretty cool. Another thing that I want to remind you of is that 5 and 6 membered cyclic hemiacetals are very common because 5 and 6 membered rings are very stable and therefore very common in nature. But the cyclic hemiacetals are especially important because hemiacetals aren't particularly stable. Typically they form and then they either go on to the acetal or they go back to where they came from. But 5 and 6 membered cyclic hemiacetals are much more stable.